Hello guys, so welcome back. So and now we will be covering the part 2 of our system design for a key value store, and we will be covering the API design, and we'll be deep diving into the major component, and we'll also be discussing why we have chosen this way versus why not this way. Okay, so let's start with that. What sort of API that will be required, right? So we'll be requiring the API like post. One is a post slash key value pairs. So key value pair is my resource. Okay, and so post and then key value pair. I will have my body. In that body, I will be having key and value being assigned there. Right. So the body will be containing the key value. So when we will be making a post request, the body will be passed. Right. Then the uh, put is used for the updating the existing. So if you know how these verbs are being used, right? Post is when, say, let's say I'm creating this first time, so we use a post verb, but put is required when we are actually updating the existing key, okay, or existing value. So it will basically update the existing key or their value, right? So I pass that as a key in the resource itself, and the value could be big enough so it could be passed in the body as well. Okay, now get get is like given a key, get me the value, so it should return me that string that has the content. So but right, so anything that we would persist into, we will return in a simplified way is a string. Okay, and whatever we are inserting also, we will be treat that content as a string only. Okay, and will be there's a get API key, and then we are having a delete. Delete is like for deleting the existing key, right? And there's another operation that I earlier mentioned, like search, providing an ability to search by the attribute of the value itself, right? So we can have a value as a JSON, and we can keep that value as in a structured format, or we can keep it as a simplified string, an opaque for that we do not understand, right? So right, so in such, if we are keeping it in a structured format like in a JSON and all, right, so we can support secondary key as operation as well also. But if I would have gone ahead with it, assuming that value is an opaque, then this secondary key won't be supported, because the value is in just a blob and opaque. We do not understand what's the content is, how it is being organized, right? Also, in that case, we won't be able to support the secondary index. But the document databases, like if you have seen the document databases, like in a MongoDB, are the one of the document databases, that, or any other document, or like in a DynamoDB, they in that the value is not actually opaque. They provide a flexibility, and the value itself could be structured in a way that these are the key, this is the name, this is the key, this is the name. And for those scenario, we can have a secondary index being created on the attributes of the values, right? Values key, and then we can also support the searching abilities across that values, right? As an example, I mentioned, let's say we are storing the car object. Key is the car ID, and the car attributes are being stored as a car object as a JSON, like a name is Maruti, date of purchase, and then color is red in the format of a JSON. So and then we can support in a filtering ability, like given this registration, get me all the car, given this color, get me all the cars, right? Those kind of an uh, uh, operation. But in that cases, we'll have, the value cannot be opaque for us, right? Opaque for us, when I say, it means value cannot be opaque for the system, right? So, so we have covered that API design. Let's now move to the major component of the system design. API gateway is just an entry point for the all the client requests. Web applications, these are the front end application as a stateless application that will be handling all the requests, and it may do all of those validation as well also. right? You may ask me why I'm keeping the web application node, what purpose they are serving, apart from just creating one more hop and adding the latency as well also. So in the web application node, we can do some sort of an authorization, whether the given that token, given this request, whether this request is authorized to access that or not, as well as we can implement a lot of other validation. The key size could be more than a 256 character, or value size could be more than a 1 MB, where this validation will be placed. So that I mean, the web application is a right choice where we will be validating those things, before we insert into the database storage nodes. Right, so that is why the web application node required, and we can bring all of those responsibility can be kept there, like authorizing that request is valid, validation, adding the validations over the request, and tomorrow if we want to bring something like premium accounts, and we want to limit only these many operations can be supported, where we will address, where we will validate those. So web application is the one of the place we can put that. Right, now let's just database option. What are the database that I would be using here? There is a two things, and one is a SQL database and there's a NoSQL database. An interviewer will always ask you and judge you whether you understand what is the difference between them, and which one is better in this context, which one suits our need better, right? So SQL databases are the SQL databases are implemented using the B plus tree storage engine. Entire data being organized in the page into the B plus tree format, and the internal node having a keys, and the values having the leaf node having the actual page, right? So you understand the read complexities for reading any of the page, right? In any of the keys goes to the log of n, right? You have to go to the tree and go to the leaf level, and then figure it out which page it has the value, and right, and so there is a log n complexity is there, and the write complexity is similar to the read complexity. The write complexity is the order of log n, right? With the Because we'll have to search across like given a key where it exists, right? So we'll have to go into the B plus tree, figure it out, and that particular page that key exists, so it's a log of n, right? Now, so that is a SQL database, and the NoSQL databases and SQL databases are generally highly consistent, and because it update in place, okay, it do updates in place. The NoSQL DB is like an LSM storage engines, right? That is an append order write operation supports, right? So that's where the read complexity is, uh, the read complexity in general, the read complexity of the NoSQL storage based NoSQL storage based on LSM engine tend to be higher than SQL due to the scanning nature of all of the key. But here we are just having a keys only, right? Given every key will be treated as a single partition, right? Because obviously we'll map into the one node. Multiple keys will be mapped to the one node onto the database, but they will be separate partition itself also, because every key will be unique, and then since we will be choosing the key as a partition key, then it will create for every key a separate partition, and at any point of the time given a key there can be one value itself only. So we may not have the we will not need to scan uh, I mean given a partition number of keys, because there will be only one keys, and probably if we have updated, then they will we we will go find into that partition only, but it will not be uh, the partition will always have one and two entries only, right? Because in the LSM storage, we don't update in place key. We just create a new key and append it, and the previous key is marked as a non-active, you can say, or dormant, you can say, right? So we do not delete in place. Okay, and yeah. So Yeah. So where were we in the case, we will be every key is a unique partition only, and the read complexity should be order of one only, right? And write complexity, as we know, the order of one as a system, NoSQL storage support, append order only, append operations, right? So in this case, we will be going with that NoSQL storage engine because we want to support very high availability as well, uh, and low latencies. And since the write operations latencies is the order of one, and read complexity we can still increase by bringing the cache in front of the system, and for the frequently accessed key we can read from the cache as well also, right? But though we in gain our case, key value storage should be order of one only from the database itself, right? uh, Now, let's just talk about what are the different strategy that we will be needing, when when we are building this database nodes, right? There can be quite a few strategy that we can support. One is that, partition strategy I was talking about. So we have chosen key as a partition here, right? So given a key, we will using that key, we will figure out using the hash and all consistent hashing, ki what partition it belongs to, and that node, that key, the request will land to that particular node. Okay. Now, given a key, we will go to that particular node. Now we may have a different strategy here of the partition. One is that leader and follower strategy, right? So for a given, let's say the Dynamo DB node 1 is a leader partition for the range of key for 0 to 25, or 1 to 25, right? And there can be other strategy as well also. One is that the leader-less application, right? So in leader and follower, we will always, the write request will always go through the one of the partition for that given range keys leader. Okay. And there will be a other follower also. Follower is required only for keeping the redundant copy of that partition, so that, in case of any failures, we can bring another partitions, and we can provide that. I mean, since we had the requirement of data reliability, we need to partition the data, as well as we have to keep the redundant copy of the partition, right? And so those are the followers. Now in the leader and follower partition strategy, we have a quite number of ways. One is that, let's say for example, for 1 to 25 range, there is a leader for that partition. There's a, let's say, partition 1, and there's a this is a leader of 1 to 25 range. Now, for every request, we can also keep very high consistency by replicating that, the leader will be responsible for all of the write. Now, for each write, we can copy synchronously to all of the follower for that particular partition before returning to the response. So in that case, uh, we are supporting high consistency, right? But we are lowering the availability. If in case any one follower node is a down, right, we will not be able to complete the right operation for a longer period of time until unless that node comes up. Or let's say I am supporting the followers at least, 3 nodes. I'll have to, so there is a, for a given a partition, there is a 3 replica for it. One is the leader, and two of them, or let's say I'm supporting 4 nodes, 4 replica for each partition. One is the leader node, and the another is the replicas of them, right? Now, for every each request in the leader follower partition strategy, if I go with a high consistency, I will have to replicate that write request to all of the node in synchronous manner, right? Although I can initiate a request in parallel to all of them, but all of them has to complete and return a response to me before I return a response to the client. But this has a pros and cons of it. The pro is we are giving the high consistency. But the con is it is reducing my availability. And how it's reducing my availability? Uh, Basically, if any one of the node of the replica is down or follower is down, I am just blocked for that request to be completed. Hence, my request, the availabilities of the system is down, right? Or I can fail that request if the one of the node is down, right? For that, but we have chosen, we are going for the high availability system and eventual consistency. So we can compromise eventual high consistency, probably rather copying, replicating the write request to all of the followers node. Probably we can, synchronously write to at least one of the node and asynchronously write to the rest of the node. Okay, so the client operation would be immediately complete. The request landed into one of the node will write into their local storage. The database node will write that write request into their local storage, into that partition, and it will replicate to one of the other node. And it will not, it will just wait for one of the node to be replicate complete before returning the response to the client. But uh, uh, it will asynchronously initiate a request to other node for replicating the data, right? Now, in this case, we have improved the availability and reduced the consistency from strong to eventual, because one, two of the node has that accurate copy, but two of the node still has a previous version of the copy, right? But uh, in the real time, in a asynchronous way, it will be updated there as well also. But I am not blocking the client operation to be completed till all of the follower has a copy of the updated key and value, right? So these are the trade-off for each of the, and so in the leader or follower. But there's another there is a one more thing that I want to discuss, is why I have chosen the leader. So leader and follower strategy versus to the other leaderless. So leaderless. So for any right, for any right, for a given, let's say there is a multiple concurrent request is being coming for a given key. There's a same clients from the different browsers are trying to update the same key at a same time, right? So in that case, it will all goes to the single leader, and using the leader, we can basically order those requests, or whoever for a given a key, we can order and block the other operation. We can take a lock on the keys, and before updating that particular key, although other key on that partition on that node, sorry, other keys on that node will go parallelly, but it's just that for a given a key, if there is a concurrent request from the same client for the different browsers, we can, avoid having a different versions of the key at that, basically I'm trying to avoid that conflicts, right? Avoiding the conflict, and using the leader and follower, because version conflict, you can say, right? It might be possible the same client using the different browser trying to update the, for a given a key, a different value in parallel. Now which one to be accepted, so that is the cons of the leaderless partition strategy, right? But in the case of leader and follower, I can avoid that, conflicts, and hence I have chosen the leader and follower. But in given a leader and follower, we can still improve that, high availability. We can, by doing the semi-synchronous replication versus doing the full synchronous replication, right? So that way we can choose which one of that, in given the leader and follower, how we want to implement that. Let's just discuss about the
So if
leader.
our application,
Yeah, go
just a
ahead.
question. So if our application doesn't require that multiple clients are writing to the same key, then leaderless will be the correct partition scheme, partition strategy.
But it can always be a
If
case,
we don't have multiple clients writing for the same key,
right? But
if there
you
aren't
cannot
multiple
stop
writes
that.
for the same key.
Right, right. Yeah,
Hmm.
but you cannot stop that case, and you cannot stop the client to do that, because if you are providing a distributed key value store
Right,
as a managed service to them, you cannot stop them to do it. Though they don't do it, but you should have a checks and balances at your side, so that if in case that case come in the future, your system does not in a inconsistent state,
right.
right? And you should have the
Okay.
way to handle that. So so I generally prefer leader and follower, but it has a cons. The leader less, what if is the leader went down for a
Mm.
given a part? So leader went down, so when the leader went down, probably that node who is hosting that particular partition leader will go down, right? And all of that partition, it is hosting, will go down. I mean, for only for the leader. Let's say the node 1 has that, for range 1 to 25 has the leader of it, and rest other partition it may have the follower only, right? So uh, for only that, partition, 1 to 25 request will be coming for the write to that particular node, right? Now if that node is down, it means that leader went down. Now when the leader is down, in now the availabilities is still compromised compared to the leaderless application. So though we have a checks and balances like, zookeeper and coordination services, that will bring the another replica, the latest replica of that partition, as a one, as a new leader, right? But it may take some few milliseconds and all, and the client operation may fail during that time, right? So I mean, how to elect a new leader, that we will discuss in that zookeeper coordination service that we have discussed, right? But let's just assume that we will have to elect a leader for that partition, and that will be on the another node, and that will take some time of it. And meanwhile, if we are supporting very highly scalable distributed key value store, probably some of the requests will fail it, right? Because that leader is down, and there now, so that is where leaderless applications are much provide very very high availability, but it has another con of it. It can have, it can have the conflicts as well also, right? Because when you do not have the leader, so so leaderless application supports quorums, and the quorums, there is a read quorum, there is a write quorums, right? And every request to be successful read and write, it has to go through the at least those quorums. So for a write request, let's say I have a three nodes. Let's say I have a two nodes, but my read plus, so it's, I mean, it should validate this condition. So if n is the number of a database node that I have in the system, and let's say R I have chosen 2, and W I have chosen 2, and n is my 3. So uh, for every read request, it will for every read request, it will make a query to two set of a node for and two replica of that partition, and then fetch all of the versions of the given that key. And similarly for the write, it can, write to at least two of the nodes before returning the response to the user, although they're supposed to write to all of the nodes. And but uh, if we have a 10 node, I don't expect, we don't want to write on the all the 10 nodes immediately. But we can have the quorums like in a read plus write should greater than 2. So at least two of the node out of a 10 node should be able to write that request before returning the client to the response. But it can write to the other nodes asynchronously to other nodes as well also. Now assume so in this case, let's say we are having three nodes, and for write request, it has gone to first to the one of the node 1 and the node 2. Okay. And let's say there is an update has come for the given the key. Now assume that node 2 went down, right? So it will make a request to the node 1 and node 3 at least, right? Now after some time node 2 comes, so node 2 has a very older version of older version of the data, the previous version. When the now let's say read request has come, the read request will query at least two node, and it has queried node 1 and node 2. So node 1 has the latest copy of that key, and node 2 has the older version of that key. Now we have a conflicts, right? We'll have to handle the conflicts, right? So in the leaderless cases, although we have able to support the high availability, because any of the node it should be able to write, right? Out of a three node, it should be able to write at least two of the node. If this I mean, if we had the quorum like an 10 nodes, and then read plus write should be greater than n, so we should be able to write to any of the, I mean, at least W of the node. And there's W of the node not necessarily be same for every time. It could be another W as well also out of the n nodes, right? So it, at some point of the time, given a key, we may have a different version of the key. We'll have to deal the conflicts, and we'll have to resolve those conflicts, right? So hence we generally leaderless application come with their cones of bringing that, conflicts of the and inconsistencies with the versions of the data, right? So we can use that trade-off. But yes, the leaderless would also bring very, very high availability compared to the leader and follower. So we may also go with that, leaderless application. In the case of an dynamo building this distributed key value store, we can go with a leaderless as well also with it, because our use case is it should be very high availability but eventual consistency. But we'll also have to implement the way how we resolve the conflicts. Okay, different versions of the given a key, we may have a different version of the value. Okay, so we'll have
And
to
this
take care.
conflict resolution has to happen at application layer, right?
Yeah, there can
At
be a
application level,
different
we have to handle
strategy
this
for
conflict.
them. There can be a different strategy. How
Right.
do we handle that? But yeah, those are the cons of it, that ideally you should discuss this with the interviews, and then take a call out of it, ki whether you want to prefer leader and follower, or whether you want to prefer leader less. But given this, we have given assumed we are bringing the high ability and eventual consistency, we should go for the leader less, though we can achieve in the leader and follower as well also high ability. But comparatively, leader less is a more highly available compared to the leader and follower. Okay, and so that's how it is. Yeah, now I think uh, okay, so we have covered API design and major component of the system design. Now, in the next session, in the part 3 of the system design, we will cover, details into the database as well as the partition lookup service. How we are maintaining the data into that, how the partition lookup service knows which node has a what IP address and all. So we will be covering those information. Okay. So yeah,